Hello, welcome again to another video lecture. In this one I have Lexi Murphy. She's coming in as my guest lecturer today. And Lexi, what are you going to be talking about?
I'm going to be talking about the kinetic molecular theory of gases.
Alright, enough of me up here. This is all Miss Murphy's show. So, take it away.
Okay, so first of all, let's just start out with a couple bits of notation here. So when you see V, that means speed. If you put a line over it, that means average speed. So obviously, it would be like taking the sum of all of the speeds and dividing by the number of particles that you have. If it's V squared with a line over it, it's actually the average of all the squared speeds. So you actually would take all the speeds and square them individually and then find the average of all of those squares. And if you take the square root of the average squared speed, we call it the root mean square speed. That's just the definition. And so what I think you guys have talked about earlier this year is if you want to calculate the average kinetic energy of something, you do 1/2 mv squared, where the v squared has the line over it. That's the average squared speed. But also something that's new in this unit is related to the derivation of the ideal gas law. The average kinetic energy is also equal to 3/2 times Kb, this is called Boltzmann's constant, times temperature. Temperature has to be in Kelvin in this equation, and Kb has a value of 1.38 times 10 to the negative 23rd joules per Kelvin. And so if you set those two equations for average kinetic energy equal to each other, and you just do a little bit of algebra to rearrange and solve for average speed squared, I did that over here. You get 3 times k times t over m. And then if you take the square root of that, it becomes the square root of 3kt over m. You could also do it instead of using Boltzmann's constant and the mass of just one molecule. You could use the ideal gas constant, 8.31 joules per mole times Kelvin. And you could use molar mass as your mass instead of the mass of a molecule. But actually, you've got to be really careful with molar mass here that it's in units of kilograms per mole, not grams per mole. So that's a conversion you'll have to make. So anyway, these different units I have written here, but you might not be able to see them from the camera. So m is the mass of a molecule in kilograms. Kb, 1.38 times 10 to the minus 23rd joules per Kelvin. T is the temperature in Kelvin. R is 8.31 joules per mole per Kelvin, and M is molar mass in kilograms. Whoops, that's not joules. Kilograms per mole. So the reason why it's really important to deal only in averages when you're talking about all of this kinetic molecular theory stuff is that not all the particles in a sample of gas are going to be moving at the same speed. And so a lot of times what you'll see is a graph drawn where on the y-axis you have the probability of a molecule having a certain speed, and on the x-axis you actually have speed. And so what you can do for a gas is graph it, and what you'll see is that you get this nice distribution where this maximum point here is called the most probable speed. And so the speed that corresponds to that is going to have the highest probability of a molecule having that speed. However, you can clearly see that there are going to be a bunch of molecules that have probability of going slower than that, and a bunch of molecules that have a probability of going higher than that. In case you're interested, the root mean square speed is right around there on the graph. It's a little bit higher of a speed than the most probable speed. But the interesting thing is that if you graph the same gas at a higher temperature, the graph will actually shift to the right a little bit. But you have to almost imagine it like you take the graph and you pull it this way. It's like a string, and it's not going to be as high anymore because it's the same area under the curve after you move it. So at a higher temperature, the most probable speed is now at a higher speed than it was at the lower temperature. And also, if you're using a gas that has a lower molar mass, that's going to have the same effect as increasing the temperature. A gas with a lower molar mass is also going to have a higher speed than a gas with a higher molar mass. So I think that's everything that you need to know about kinetic molecular theory of gases. Thank you very much.
Just really quickly, why is the root mean squared velocity higher than the peak?
Because when you go through, because you're squaring the number and then taking an average of it, all of the big numbers have a bigger effect on the average because when you square them, they become really big numbers.
All right, so I just want to touch on a few things that Ms. Murphy talked about really quickly. Here is the graph that she drew up on the board. And for different temperatures, different thermal energies here really is what we're looking at. There are certain speeds for each molecule, or most probable speeds for each molecule. So now, if we double the speed, we expect the energy to be 4 times as great, or quadruple. So here we have that just happening right here on this graph. And while the most probable speed increases, the percentage of molecules at that point, at that speed, decreases. Because remember, temperature is the average kinetic internal energy there. So we don't need to have all the molecules moving at that speed, but overall, the curve kind of slopes down. So just kind of wanted to look at this a little bit more in depth, just kind of based off of that. So there it is. Here we're looking at the average kinetic energy. That's what it means when we have the bar over it. Once again, that means for the average. And here we just have for the average kinetic energy per particle, for particles within a gas, depends on the mass of the particles, and the root mean squared velocity. And that's squared, again, kind of the same kinetic energy idea. And this relates to the Boltzmann constant times the temperature. So we can use that information to go back and forth between energy and temperature. And that's a very helpful relationship as we're moving forward throughout looking at the particular molecules. And now what happens when work is done or when the pressure changes as we look into Chapter 15 in thermodynamics a little bit more. All right, 2 quick questions from lecture tonight. First, I want you to use the internet to find an equation for average speed using temperature, the gas constant, and molar mass. So for average speed, I would just try using the idea of kinetic theory of gases or kinetic gas theory, either one, and look under it. For the big thing here is that you want the average, not the root mean square speed. You really want to please find that average speed. It's a specific thing, a specific formula, and I'm going to tell you right now that it involves the number 8. So there, hint. Excellent. And then second question, what at the coldest temperature ever observed on Earth, 129 degrees, negative 129 degrees Celsius, what is the root mean square speed of nitrogen molecules? First, you're going to need to convert to Kelvin, and then one nitrogen molecule is 28 molar mass. It has 20. Each nitrogen molecule has a atomic mass unit of 14, and 2 atoms make up 1 molecule. So use that information and tell me what the root mean square speed of nitrogen molecules are. Thank you very much, and have a good night.